Welcome back. Last two climate controls, proximity to water and topography. It's a little bit different than the talk of ocean currents being near water relative to ocean currents, because this could technically be also other large bodies of water, larger lakes like the Great Lakes, larger inland seas, the Caspian Sea, even the Mediterranean Sea, things that don't typically have these ocean currents as well. But we will also talk about ocean, so just a little bit different than ocean currents. And then also topography, the terrain. So let's take a look at a couple of cities. About the same latitude, Reykjavik, Iceland, so right on the Atlantic Ocean, and our old friend Yakutsk, Russia, pretty far away from any water source. So again, proximity to water, you have to be pretty darn close. So Yakutsk is, pretty far away. So let's look at the difference. So again, about the same latitudes. In fact, Iceland is a little bit higher latitude. But look, this far away from the equator, you should have the latitude, with being so high, you should have a large fluctuation in temperature range. The further you get away from the equator, the more your highs and lows range. Well, it's not really the case in Iceland. And then same thing with precipitation. Generally a decent amount of precipitation. Really the difference, they both have low elevations. They both have very low elevations. So it's just something about being in the proximity of water that kind of moderates the temperature ranges of Iceland. So the reason being, land heats and cools faster and more intensely than water. So it heats up real quick, but it cools down real quick. So continental locations away from water have a larger seasonal temperature range than maritime locations closer to the ocean, because maritime locations often have more precipitation because of their proximity to a large moisture source, the ocean, but they also have smaller temperature ranges, less fluctuation, because while land heats and cools faster than water, water heats and cools slower. So while land can heat up a lot, but it's going to cool down a lot as well, daily and throughout the year. Well, water, it takes a long time for it to heat up, but it takes a long time for it to cool down. It takes a long time for it to heat up, a long time for it to cool down. And so if you're in proximity to water, and that water is also affecting the air temperature as the air and the ocean surface interact, it's helping to moderate that temperature. You're not going to get these big swings back and forth like you would be on land. So again, looking at a couple of different locations. About the same latitude, we have Seattle, and we also have Mongolia. So now there's an elevation difference as well, so we got to consider that. But again, but that temperature range is just so big, because again, Seattle, right near the ocean. Seattle's right near the ocean, so you're not going to get as much fluctuations. Whereas Mongolia is inland, far from any ocean, far from any large body of water, so you're going to get a large fluctuation. Right? Because again, water heats up slowly, but it cools down slowly. So you're getting, locations near large water sources are pretty consistent, or I should say at least has a smaller range than anything comparable at the same latitudes if it's away from water. So water has this moderating effect on temperature. And then what about topography? So the terrain, the shape of the land can also affect the climate. So here is the state of Washington. Seattle is right around in this area here. So we're looking at, Seattle is pretty much right at sea levels, right at the ocean. So low elevation. But if you look at the rest of the state of Washington, there's low-lying areas. These brownish parts are mountainous areas. There's a high, flat desert plateau over here. So over on this side of Washington, very lush, very green. Same with the mountains, but then you go up and over the mountains, and it's very dry desert. It's horrible. I spent some time here doing some research up here, mostly on the volcanoes and on the coasts of Oregon and Washington. Lush, green, temperatures, mild temperatures, small fluctuations because it's near water. There's a cold ocean current, so typically cooler temperatures, but a lot of moisture as well. But then you go up and over the mountains and it's hot, dry, funky. Ugh. It's like here. What's going on with that? Well, so let's look again. Here's Seattle, so right at kind of sea level. But we're going to take an imaginary path east over Washington. And you can imagine the city of Bering would be right here, higher elevation. Stevens Pass, that's up in the mountains. And then as you get up over the mountains, Waterville, where my mouse go, Waterville, so lower elevation. Wilbur kind of plateauing off, Spokane plateauing off. So again, you can imagine from Seattle, from the coast, going up over the mountains. This is a cross-section, a slice of Washington. If we were to slice it in half and look at it from the side, what would the terrain look like? So from sea level, if I'm heading east, you go up and over some mountain, and then you get to this flat part. Well, this topography, this terrain, influences the climate, specifically the climate of what's going on this flat desert plateau on the eastern side of Washington. So, high mountains, like the Cascade Mountains, which is what runs through Washington, can act as wind barriers. Now, we're talking large mountain ranges. We're not talking about like, oh, the White Tank Mountains, and the Estrella Mountains, and South Mountain, and Camelback Mountain. These are tiny little baby mountains. We're talking mountain chains. Rocky Mountains, Appalachian Mountains, Himalayan Mountains, Cascade Mountains, Sierra Nevada mountain ranges. These are broad, big mountain ranges, not just little baby hills here and there. But in any case, high mountains, again, act as wind barriers. So mountains cause precipitation if they lie in the path of rain-bearing winds. So you get this wind coming off the coast of Washington, has a lot of moisture in it. That's why it rains a lot in Seattle. As that air hits those mountains, that's called the windward side of the mountains, that air is forced to rise up and over the mountains. As air rises, it cools down. As it cools down, it holds less moisture. Because this goes back to the thermodynamics and physics of air, cold air can hold less moisture. So if there is any moisture in that air, as it begins to cool down, it has to let it go. It has to drop it. So it has to rain. So that's why on the west side of Washington, you get all this rain, especially as that air mass is moved upward. It's cooling down. Cold air holds less moisture, so it rains a lot. So now when it gets up and over the mountains onto the other side, called the leeward side of the mountains, now the air, as it kind of descends, begins to warm up. But as it's warming up, it's becoming warmer, but it's dry. It lost all its moisture over here on the other side as it was going up and over the mountains. So as it descends, it's warm, dry air. So any air that kind of just goes off to the east side of Washington is warm, dry air. Hence, if you have dry air over an area, you're going to get a desert. So that's kind of what's outlined here. Again, as air is forced to rise over a piece of land, large mountain ranges, not just little single mountain ranges, but large mountain ranges. We don't really have those here too much in Arizona, at least down in the central or southern portions. But the temperature decreases, precipitation increases. Again, that just goes back to cold air having the ability to hold less moisture. Once that air mass goes up and over, temperature increases, but the precipitation decreases because there's just no moisture in there. And it creates something called a rain shadow. A rain shadow. So, we can picture the elevation is high here. That's where the Cascade Mountains are. So they cast what's called a rain shadow on the east side. Very little precipitation. So let's see how that looks out. So let's focus on the blue precipitation. I mean, there's temperature fluctuations, yes, but all of these locations are right around 48 degrees north latitude. Yes, their elevations are different, so that does change the temperature ranges, but let's look at the precipitation. So Seattle, you get a decent amount of rain there throughout the year. Bering, Washington, a little bit more. It's because as this air is rising, it's going up in elevation, it's cooling down. Cold air holds less moisture, so it's dumping some of that moisture. And as it gets to a high point up and over the mountains, again, you're dumping a lot of that moisture. But by the time that air mass gets to the other side, you can see temperatures have been getting cooler and cooler and cooler, rain more and more and more, but once you get to the other side, as that air is descending over the mountains on the leeward side, where the rain shadow is, now the temperatures are getting warmer, and the precipitation is getting less. Warmer temperatures, precipitation less. Warmer temperatures, less precipitation. So over here, we have a high desert, and that's in the rain shadow of the Cascade Mountains. Yeah, so not all of Washington is lush and green and nice, just the coast. just the coast, just this third of it near on the west side of the Cascade Mountains. You go up and over it, dry, funky, hot, high desert. Ugh. In any case, those are the 6 controls of climate. Again, that is, understanding climate in general it takes years to study, and I gave it to you in 3 little weird videos. So by no means is that everything that, every factor that you can determine a climate with. Those are kind of those 6 main climate controls, though, latitude being number 1, but all of those things go into shape a climate. For instance, our climate here in Arizona, the latitude, or at least in the Phoenix area, the latitude, the elevation, not near any water, the wind patterns, the topography of the area, all of that plays a part in our climate. So it's very complicated. Climatology, meteorology, which is the study of weather, is very complicated. You have to understand and take a lot of physics. It's kind of the main science you need to take in order to become a meteorologist or climatologist, because there's just so much going on, so many parts interacting. Plus, you also need to know a lot about our next section, energy. Energy is a fundamental concept in physics. Another reason why meteorologists, climatologists need to take a lot of physics. But I'm not assuming that we're going to be meteorologists or climatologists, but we do need to talk about energy. So that's what we'll talk about when we come back. See you in a second.